Welcome to the webinar on hydraulic elevators busting the myths. This webinar is intended to clear some misunderstandings about hydraulic elevators by presenting basic facts and busting some of the myths around hydraulic elevators. It tries to declutter some technical things and highlight best practices so that problems can be avoided. Some of the myths surrounding the hydraulic elevators mainly revolve around hydros being not heat resilient, and thus not an ideal choice for installations where it's generally warm. Concerns have been raised by the MRL and gearless lobby about hydros being energy inefficient to environmental danger due to presence of mineral oil. Again, the belief that servicing a hydraulic installation is complicated and not everyone's cup of tea is very common among those who hardly understand the technology. It is logical that such myths are a result of lack of understanding and wrong approach. When enough clarity on any matter is missing, wrong conclusions are derived which ultimately become myths. In the coming webcast, we confront a few of such myths listed here by presenting facts so that a better understanding can be developed. One of the most popular myths that's often debated is that hydraulic elevator doesn't function good in a warm climate. If this would have been true, then the facts tell something else. Hydros are the most installed elevators in hot Mediterranean regions like Greece or Italy in Europe, or function perfectly fine in some of the warmest places in United States of America like California for example, or to that matter in the Middle Eastern countries and Southeast Asia. Statistics available from government records and elevators and escalators associations worldwide indicate very clearly that the installation of hydros is not influenced by regions or climate. It is very much true that oil viscosity changes with change in temperature. However, it is worth asking the question, why should the oil temperature rise and which influencing factors are often overlooked? The answers lies in not one but many things that can unnecessarily influence oil temperature. Let's try to understand them. Since oil as a medium comes in contact with each and every component in a hydraulic circuit, it is the single most influencing element. Let us understand first what kind of problems arise due to rise in oil temperature. The effect of high temperature directly impacts the viscosity of oil. Thin oil results in more flow through small preset orifices in the control valve and increases the internal leakages in pumps. That affects the volumetric efficiency of the component. The aftereffects have a domino effect on the system. Hard starts and stops of the elevator cabin experienced with erratic travel characteristics result in unpleasant travel experience. The cabin overshoots the floor level. Prolonged heat also accelerates the oxidation process in the oil, degrading its properties and reducing the lifespan further. So now that the side effects of hot oil are known, let's look at what causes the oil temperature to rise unnecessarily. The matrix highlights four important facets. A wrongly adjusted control valve with excessive bypass and leveling settings. Pressure drops arising due to long piping and sharp bends in the connecting pipe used to connect the power unit to the hydraulic cylinder. The elevator traffic is very high and the generated heat cannot be dissipated quickly. The machine room where the power unit is located is not adequately ventilated. The overall ambient temperature of course has some effect on the oil viscosity. However, the highlighted four factors are man-made whereas the ambient temperature is more of an environmental influence in which the power unit is operating. Let us see the practical impact of the causes just discussed. A hydraulic system using mechanical valve generates most heat in the bypass and leveling phase, wherein the pump and motor is delivering the constant flow to the valve and most of it is being sent back to tankers. The elevator only moves slowly to provide the gentle start and smooth stop to passengers. Ideally, such a bypass phase has to be as short as possible in order to transform the energy positively. Heat generation happens when the transformation of energy doesn't result in positive work. The law of thermodynamics clearly state that energy can be only converted from one form to another, it cannot be created or destroyed. Hence whatever is not converted into positive work by moving the cabin at full speed during the bypass and leveling phase, gets converted into heat as the oil is bypassed back to the tank. A proper bypass adjustment with a set time of maximum 1 to 2 seconds should be adequate enough to prevent the oil temperature to unnecessarily rise. The piping from the machine room to the cylinder is often less than 5 meters. However, quite often bends and adapters are used to interconnect different piping elements. Care should be taken to avoid unnecessarily long piping, sharp bends and reduces. Using smaller diameter pipes with sharp bends and reduces makes the oil flow turbulent, which increases friction within the oil layers and the equipment. This pressure drop translates into heat, which can be very much avoided by sticking to best practices in hydraulics. Depending on the flow, the piping size should be adequately selected. In case where long pipe connection is unavoidable due to the location of the machine room, metal piping should be used. The correct valve selection influences the heat in a big way, especially when the hydraulic elevator is handling heavy traffic. As explained earlier, heat generation happens when energy conversion doesn't result in positive work. This happens mainly in the bypass and leveling phase, where a major portion of oil delivered by the pump is sent back to the tank in order to run the elevator at slow speed. Thus, an elevator running on mechanical valve handling 25 to 30 starts an hour, most possibly in a public place like mass transit system or shopping malls, can quickly cause the oil to heat up due to frequent bypass and leveling with every start call. In the absence of proper ventilation and cooling, the elevator may start experiencing erratic travel characteristics as soon as the viscosity of oil has changed. Constant high usage leaves very little time for oil to cool down, thereby even worsening the travel comfort. Though mechanical valves are most suitable for home and low to moderate use elevators, it is highly recommended that VVVF valves should be used in such applications, where the inverter regulates the motor pump duo, which in return delivers the right quantity of oil needed in the bypass, acceleration and leveling of the elevator. This results in positive energy conversion. Not only is such a system up to 60% energy efficient, which saves money, but it also offers excellent ride quality by compensating for increase in temperature and load in real time, guaranteeing superior ride quality consistently throughout the elevator operation. Further advancements in inverter manufacturing have resulted in affordable prices, bringing the break-even point or return on investment to less than 3 years, offering lifetime savings and excellent travel comfort. Most of the heat generated is dissipated in the machine room. Therefore, it is extremely necessary that the machine room should have adequate ventilation. Having cross-ventilation helps a lot in keeping the power unit cool. In practice, however, machine rooms often have exactly the opposite conditions, like poor or no ventilation, power units stacked in some corner very near to walls, inadequate or no cooling at all. No wonder in such instances, the ambient temperature surrounding the power unit is much higher than what it should have been, as the dissipation of heat is either very less or next to nothing. This contributes in heat generation and related problems, especially when the elevator is frequently used. Example pictures showing placement of power unit either directly in a machine room located next to the elevator shaft, or in a closet cut out in the elevator shaft itself. In both the cases, with every cabin movement, air is automatically blown from the shaft on the power unit, providing natural cooling. In case if the machine room is poorly ventilated, at least the power unit should be placed leaving sufficient distance from the walls, so that air circulation can happen. A simple cooling fan, or if need be an oil cooler, can be installed to keep the temperature under control. An exhaust fan blowing the hot air out of the machine room could be really helpful as well. Selecting the correct oil viscosity grade suiting the elevator application depending on the ambient temperature and elevator traffic is as well very important. The correct viscosity grade of oil is the primary deterrent against unwanted travel comfort. If the oil itself is less prone to change its viscosity with change in temperature, other means of keeping the oil temperature under control may not be even necessary. It is a general practice that regions where the normal climate is hot tend to use VG68, whereas VG46 is more preferred in Europe, where ambient temperature is moderate to cold. However, the elevator traffic is also equally important. Frequently used elevators should use higher viscosity grade oil. The higher the viscosity grade, the less the oil tends to change its viscosity when it gets hot. Likewise, higher viscosity oil may be unsuitable for colder climatic conditions, like for example in Northern Europe where the temperature drops below a certain threshold in winter. For easy reference, a table provided here should give reference in selecting the correct oil type. Having seen the effects of oil temperature on the hydraulic elevator and the reasons that causes the problems, it is clear that warm climate and hydraulics have nothing to do with each other. If the mistakes can be avoided in the first place and best practices followed, all the problems can be addressed. The failure is an outcome of lack of technical understanding and oversight that causes the system to fail, giving rise to the false notion that hydros cannot operate in hot climate. The underlying fact is that as long as the oil temperature and viscosity is maintained, the system works perfectly fine. Let's look at another myth, that hydraulic elevators offer poor travel comfort and jerky starts and stops. Once again, such conclusions have been an outcome of unpleasant experiences from poorly designed systems, where best practices and design principles have not been followed. Very often, to cut costs, industrial hydraulic valves are used in hydraulic elevators. Such valves may be good for the objective they are designed for in the general industry, but are not suitable for the vertical transportation domain. Industrial flow control valves differ in design with respect to their counterparts in the elevator domain. Industrial valve design is based on modular functionality for handling much less flow, and have no integrated safety options as they are not designed for handling passengers. High pressure losses, unavailability of adjustments to adjust travel comfort, absence of pressure compensation, ability to work across a wide pressure and flow range makes them highly unsuitable for elevators. Mechanical flow control valves designed for elevators offer excellent ride characteristics. Servo-electronic valve, due to closed-loop system and electronic control, offer superior ride quality by compensating for changes in pressure and temperature. For high traffic, VVVF system offer even more advantages in reducing heat generation and being energy efficient. Poor travel characteristics and comfort can also originate from the valve adjustment. As explained previously, correct valve adjustment is the key for getting the optimum ride comfort and preventing unnecessary oil heating. After the installation and during the trial runs, proper care should be taken to fine-tune the valve, adjust the bypass time, transition and deceleration into leveling and stopping to ascertain the best ride performance. Elevators are programmed to re-level whenever the distance between the cabin and landing door deviates beyond a set threshold. Such a re-leveling system helps position the cabin exactly at floor level so that going in and out doesn't present problems for passengers. Entrapped air in the hydraulic cylinder mostly influences the floor landing accuracy, especially during loading and unloading. As air is highly compressible, its compression in the hydraulic cylinder during loading of the car results in sinking of the elevator cabin. The result is further magnified in indirect system, wherein a small movement of the hydraulic cylinder results in double the cabin movement. The reverse happens when the loaded cabin is unloaded at the floor level. Removing the load results in compressed air to expand back, thereby pushing the cabin up from the landing door position. Although re-leveling system takes care of the problems, air shouldn't be present in the system in the first place. It is very important that air is bled from the cylinder head after the installation and first few trial runs, and later if stopping accuracy of the cabin is experienced while loading and unloading of the car. Likewise, internal leakages in the hydraulic valve due to contamination and wear and tear of oil seals can also result in sinking and re-leveling problems. Changing the damaged oil seals usually addresses the problem. However, if proper oil hygiene standards are followed from the beginning and adequate ingress protection is available in the system, contamination can be prevented from entering the system in the first place. Likewise, presence of air in the hydraulic circuit can be completely avoided by adopting to industry best practices. The outcome of poor performance of industrial valve, entrapped air in the hydraulic circuit with frequent re-leveling due to it and internal leakage due to contamination in oil can result in poor travel comfort or even sinking. However, The problem is a result of deviation from best practices and standards and not due to any inherent flaw in the elevator hydraulic technology. As such, the explained facts must have helped bust the myth. Everyone owes its share in protecting the environment. There is no doubt that climate change is one of the biggest problems that affects everyone. Every industry has the responsibility to correct mistakes and improve products that are environmentally friendly. However, the concept has been as well misunderstood and misused to misguide people. This myth is exactly about such a negative propaganda that hydraulic mineral oil used in hydraulic elevators is an environmental disaster. The facts are rarely debated. How can a few liters of oil in a tank that has a very long lifespan become environmentally unfriendly? If proper care is taken, the oil can last even longer than 10 years and does not need any replacements. As long as the oil doesn't spill, it doesn't come in contact with the environment and create any damage. Quality product suppliers following industry best practices incorporate the necessary elements in their design which safeguard oil leakages. For example, a cylinder head design should have provisions to collect oil droplets from the cylinder head and drain it back to the tank should the cylinder oil seals wear out in worst case. Very few think about eco-friendliness of the complete equipment. Just taking an element out and branding it environmentally unfriendly simply because hydraulic elevators has mineral oil in tank is not correct. A life cycle analysis, or LCA as it is popularly known, of the complete elevator is a true indicator or measuring scale for assessing the eco-footprint. Research and published reports prove that hydraulic elevators have a far better LCA result than gearless or traction elevators. A comparison showing hydraulic and traction elevator can be seen here. A hydraulic elevator gives up to 43% less impact to the environment for modernization given the fact that complete life cycle from raw material through assembly, installation, usage, maintenance and end of life is taken into consideration, and up to 7% less impact than traction in case of new installations. For applications where the local environmental regulation mandates the use of biodegradable substance, enough choice of biodegradable oil is available. Biodegradable oil meets the same performance characteristics as mineral oils with respect to viscosity and flow at given temperatures. It also offers excellent anti-wear and corrosion protection for pumps and valves. Numerous tests carried out by system integrators have proved that biodegradable oils can be comfortably used as a replacement of mineral oil should it be absolutely necessary. Among the most commonly available biodegradable oil available in the market, a few have been listed here. Almost all major oil companies sell biodegradable hydraulic oil thanks to its ever-increasing popularity. From vegetable-based hydraulic oil to synthetic ester, the market is full of choices. Depending on the viscosity grade, finding a suitable biodegradable oil is relatively easy given the big choice. Having eco-friendly products is the need of our time. The irreversible damage mankind has caused on the environment cannot be defended presenting any arguments. However, using this as marketing tool has been perfected by the industry for its own good. The philosophy that anything that carries an environmentally friendly sticker is good and hydraulic elevators are environmentally unfriendly is a one-sided argument based only on marketing arguments presented by some elevator companies willing to profit from traction and gearless elevators. The facts and arguments presented so far should be enough to bust this myth. As energy prices go up, products in every industry are vetted on how much energy they consume. Consumer products have an energy label even indicating their energy class so that consumers are well informed before making choices. Presenting the products as energy efficient boosts the marketing and sales argument very well. Often how the product that claims to be energy efficient is overlooked and the method in which energy classification should happen is one-sided and flawed. Hydraulic elevators are assumed to be energy inefficient. Facts like motor size of traction and gearless motors being considerably smaller than the hydraulic elevator motors for the same payload is presented to prove the point. Although the bare numbers might give an impression of this being true, but such comparison is never an apple-to-apple comparison. Traction and gearless elevators use counterweights to offset the static load of the elevator. Hydraulics don't. No wonder the motor size is smaller. Modern-day gearless elevators use inverter drives. However, such comparison results intentionally pitch gearless inverter drive with mechanical valve-driven elevators. No doubts the results are in favor of gearless in that case. Though gearless motors might be comparatively smaller and draw less energy, but this happens in both the up and down direction of the elevator. Whereas hydraulic elevators don't need motor power in down direction as it's gravity assisted. Gearless elevators need costly automatic rescue devices commonly known as ARDs with large expensive batteries. Hydraulic elevators can be manually lowered or need a simple 12 volts or 24 volts inexpensive battery supply to do the job. Using counterweights and inverter drives in hydraulic elevators can reduce the motor size and energy consumption by up to 60% and thereafter leave no difference between the gearless and hydraulic. However, clever marketing tactics by the traction industry hides these facts and presents only what is suitable for its own good. Between the different drive technology available in the hydraulic elevator industry, it is but obvious that the VVVF-driven system is the most energy efficient. The reason is well clear from the illustration seen. The mechanical valve and servo-electronic valve work with continuous flow pump motor wherein oil needs to be bypassed in the slow speed mode. The VVVF system, on the other hand, supplies just the right quantity of oil needed in the different traveling phases so as to have near zero bypass. This is done by changing the frequency of the motor so as to have it turn at different revolutions per minute, in return getting variable oil flow from the pump. Not only is energy consumption matter taken care but also the heat generation as well. VVVF system is easily justified for high-usage elevators, where energy savings can be substantial and return on investment can be achieved in less than 3 years. The underlying fact is that even hydraulic elevators can be energy efficient if the right drive is selected. A hydraulic home elevator consumes more or less the same power a typical household appliance consumes. The table provides an approximate comparison with respect to various other common household appliances. It once again emphasizes that hydraulic elevators cannot be red flagged on the energy consumption matter. Energy consumption can be further reduced by modifying the travel speed. By simply tweaking the up and down travel times, motor size can be reduced further. Up direction travel needs motor power. Faster up traveling needs a bigger pump and motor, effectively consuming more energy. However, as hydraulic elevators don't need any energy in the down direction, speed can be increased while coming down and reduced while going up. The overall travel time would still remain the same, but tweaking the system in this way would reduce the motor size and effectively result in reduced energy consumption. The table provides a comparative study in energy savings. Decisions have to be based on facts, calculations and above all on realistic comparisons. The myth that hydraulic elevator is not energy efficient should be addressed by now from the facts and arguments presented so far. Just because hydraulic elevators use hydraulic oil, it doesn't have to be oily and messy in the elevator shaft or machine room. Unlike the misunderstanding that oil spillage is normal in the hydraulic elevator shaft, in reality it is just as clean or as dirty like any other elevator shaft. Oil used in hydraulic circuits travels through pipes and fittings and doesn't leak or spills around just like that. Oil leakage can cause spillage either if there is any oil seal that has worn out or the installation has been done unprofessionally using substandard quality material or ignoring industry standards and best practices. Products from quality manufacturers use high-quality seals and have design redundancy to deliver fail-safe operation even in not ideal situation. However, contamination and wear-tear can lead to component failure over a period of time. Nevertheless, a typical system design has enough measures to collect the oil if it were to leak and drain it back to tank without causing any mess. An example of a hydraulic cylinder wherein the oil drainage port on the cylinder head is available but isn't connected with a simple pipe to drain any oil which may come out of the cylinder head back to the tank. In the event of cylinder oil seal wearing out, such ignorance in installation could cause the oil to leak from the cylinder head and accumulate in the elevator shaft. This is easily avoidable by simply connecting a drain pipe. Flexible hose pipes are the most preferred connecting elements in a hydraulic elevator. The flexibility to bend and twist makes the hosepipe quite easy and practical to use. However, overdoing the bending beyond a certain limit can cause hosepipes to damage and result in failures. The weakest point in the hosepipe is the metal crimping, which is basically a joint where the rubber hose comes in contact with the metal connector. Bending the hosepipe with tight radius results in undue stress and eventual failure in the long run. Such a failure can not only be a risk to the hydraulic elevator but also a reason for oil spillage. Once again, by following best practices, such failures can be easily avoided and leakage prevented. If the wrongdoing while installing the hydraulic elevator is addressed and best practices followed diligently, oil spillage is a myth. A few examples and explanation presented so far should be enough to differentiate the myth from the fact. Everything is complicated or easy. Classifying things into categories is an individual perception and doesn't necessarily mean that it aligns with everyone's views. When we try to do things without proper understanding, it is obvious that we find it complicated. Let us look into this myth and try to understand what is really complicated. A traction or gearless lift, when compared to a hydraulic lift, has many more components. The installation and maintenance take much longer than hydraulic elevator. There is no counterweight in hydraulic elevator, and with that no counterweight safety, guide rails, counterweight buffer, counterweight carriage guide shoes, etc. In hydros, the machine room is mostly on the ground floor besides the shaft. Nothing heavy has to be carried through the building on the top. Whereas a heavy traction or gearless machine has to carried and installed on the top of the shaft in case of traction elevator. So what seems more complicated now? A hydraulic system is a simple assembly of a pump, motor and control valve with respect to the tank. Once installed and connected to the cylinder, the system runs maintenance-free for years. Servicing if needed is about changing oil seals in the control valve, that is again done in matter of minutes standing in the machine room. The system has too few components to make things complicated. A lift technician has to fundamentally understand some basics do's and don't while working on the system. No specialized know-how or skills are really necessary. In fact, most parts used in the complete hydraulic elevator are open market components. Even oil seals are mostly standard items which can be procured from the market. Gearless or traction system, on the other hand, need the technician to do maintenance on the machine, which is placed on the top of the elevator shaft. More components make the job difficult and require special skills. Research studies and statistics published on assessment of damage on elevators after earthquake have proved without doubt that hydraulic elevator is much safer and prone to very little or no damage in case of a natural calamity like earthquake. Massive inertia loads set in motion through building sway combined with the heavy main drive on the top of the building present a big danger to the passengers in case of a seismic tremor. The counterweights in such situations sway out and can potentially hit the car, injuring passengers. The hydraulic system, on the other hand, doesn't have counterweights and the hydraulic cylinder is positioned on the ground. The reduced inertia load with the elevator load is completely carried by the foundation of the building. Possibility of major damage or injury is greatly reduced, conceivably by a factor of 10 to 1. In the event of fire, the smoke tends to rise, obstructing access to the evacuation equipment situated on the top of the elevator shaft in case of gearless elevators. Whereas, the hydraulic elevator machine room is situated on the ground floor, making any rescue very easy and safe. By simply turning the emergency manual lowering, passengers can be rescued by lowering the cabin to the ground floor. No electrical power is needed for rescuing. Alternatively, hand pump available on the valve can also let the cabin be pumped up in case of flooding of the shaft. The facts presented so far not only prove that the notion of hydraulic elevator technology being complicated is a big myth, but also further highlights the facts that hydraulic elevators are the safest in case of natural calamity or fire. It should be by now clear that lack of technical understanding, know-how, and in most cases, ignorance has resulted in the myths creating fear in the minds of people who have developed a false picture about a technology which is most widely and successfully used in the general industry. Should hydraulics as a technology would have been flawed, then from the basic machinery to complex automotive, from maritime ships to high-tech aircrafts and even spacecrafts would not have reliably functioned. Elevator hydraulics is a relatively easy science when compared to other domains where hydraulics reliably functions in the most challenging conditions. In fact, most of the things would only function because of hydraulics and there's no alternative to it. Evaluation of facts should be based scientific facts and engineering fundamentals and not on beliefs and myths which are physiology-driven and often twisted. Please do not hesitate to contact us should you have any questions or need further clarifications. We thank you for your time and interest in Blaine Hydraulics. If you liked this webcast, please do not forget to like and subscribe our YouTube channel.